Hello everyone and welcome to this new video. We are going to explore Unigram tokenization. So unlike the rule-based splitters you might be familiar with, Unigram is a subword tokenization algorithm that relies on probabilistic model. You will often see it used in combination with like SentencePiece, which is the implementation powering major LLMs like Albert, D5, mBART, XLNet, etc. One distinct feature of this approach is how it handles input. SentencePiece addresses the fact that not all the large languages uses space to separate words, for example, Chinese and Japanese. It iterates the input as a raw stream, including the spaces in the set of characters. This allows the model to be fully language agnostic. So to understand the Unigram, it helps to construct it with the algorithm like BPE or WordPiece. Those algorithms are bottom up. They start with the individual character and merge them together based on the frequency to create the vocabulary. But Unigram works in the exact opposite way. It's a top-down approach. We start with a massive vocabulary, much larger than what we actually want, and we systematically remove tokens until we reach our desired vocabulary size. It is a process of refinement rather than construction. So we start big and then get smaller. How does the model makes decisions? It relies on the Unigram Assumption. The model considers every token to be independent of the token before it. It is the simplest form of language model. Mathematically, consider every token to be independent of the token before it. The probability of the specific sequence tokenized word is simply the product of the probabilities of each individual token in that sequence. While this ignores context, meaning it doesn't know that new is often followed by York, for example, New York. This simple probability score is actually what we need to determine the most likely way to split a word. So, how do we determine the probability of a specific token? For example, UJ. It's based on the frequency. We look at the original corpus and count how many times that token appears. Then we divide it by the sum of all frequencies of all tokens in the vocabulary. So 20 divided by 210. So we get the probability of 0.095. This ensures that all probabilities sums up to 1. So when we have a word and we need to tokenize it, our goal is to find the segmentation that has the highest probability. Intuitively, the model usually prefers segmentations with fewer tokens. Because probabilities are numbers between 0 and 1. When you multiply numbers between 0 and 1, the result gets smaller. Therefore, a segmentation with fewer tokens involves fewer multiplications, generally resulting in a higher final score. Let's look at a concrete example to better understand using the word bug. In option A, split this into 3 characters, P, U, and J, to score this, we multiply probability of P, U, and J. So in our example, data or corpus, this results in a tiny score of roughly this number. Here in option B, it's split between P, U, and J. We do the same things, and then we get this score. Because this has a higher segmentation, a higher probability, it's the better segmentation. So in the bug example, it was easy to check every possibility, but for long words, checking every possible combination of splits is computationally impossible. To solve this, we use the Viterbi algorithm. We usually visualize the word as a graph where branches connect characters if a subword exists between them. The algorithm is a dynamic programming algorithm that moves from the beginning of the word to the end, keeping only the best scoring segmentation that ends at each position. This allows us to find the optimal path without checking every single combination. Now that we know how to tokenize, how do we train the model to get the perfect vocabulary? We'll use iterative loop. We start with big vocabulary, and then we compute the total loss over the data using the current vocabulary, and then we figure out which symbols are less needed and remove a percentage of them, and then we repeat. We do this until we hit our target vocabulary size. To optimize, we need to define the loss. In Unigram, the loss is the negative log probability of the likelihood of the corpus. We take the probability of every word in the corpus, calculated using the method we just discussed, and take the negative log of that score. We sum these up to get the total loss. We use logarithms because adding logs is numerically more stable than multiplying tiny floating point probabilities. So the critical step is deciding what to delete. For every symbol in the vocabulary, we calculate how much the total loss would increase if we removed that symbol. If removing a symbol causes the loss to spike significantly, it means that that symbol is essential, so we keep it. If removing a symbol causes almost no change in loss, meaning that there is a valid backup segmentation, we prune it. Because this is computationally costly, we don't remove one at a time. We typically remove like top 10% or 20% of symbols that have the lowest impact on loss in each round. However, we strictly never remove the base characters, ensuring we can always build any unknown word. So to wrap up, Unigram offers a sophisticated alternative to greedy merge algorithms. It uses math to find the global optimum for segmentation, unlike BPE's local merging. And through the Viterbi algorithm, it ensures we always find the best segmentation for a word. It's also flexible. By starting huge and going down based on the loss, it creates a highly efficient vocabulary tailored to the specific data. So this is, as we said, computing this each one is very slow. each like one by one. So we use the hyperparameter p, as we said, like we typically do 10 or 20%. What we have to mention is that to start, the SentencePiece is often uses an enhanced suffix array to efficiently generate that initial massive vocabulary. And ultimately, let's see. Okay, we talked about this. You can pause the video and read this slide. We already talked about it. So ultimately, Unigram doesn't just cut words, it models the probability of language itself by treating tokenization as an optimization problem rather than a strict rule set. It allows the modern LLMs to navigate ambiguity and represent complex text with much greater nuance. So that's it for this video. In the next one we will try to code one. So thank you for watching. Please like and subscribe.